Cross-region communication is often a challenge when working with isolated VPCs. Traditional approaches either rely on public IPs or complex VPN setups that don't scale easily. Instead of exposing our services over the public internet, we can build a private mesh using Headscale, Tailscale, and WireGuard to route our traffic securely across Vultr VPCs. Hello everyone, I'm Sanskriti Harmuk, a developer relations at Vultr, and in today's Tech Talk, we will look at how to create private encrypted connections between Vultr regions using a lightweight dynamic peer-to-peer setup. We'll start by understanding why cross-region connectivity matters, walk through the core architecture, and finally we'll dive into a hands-on demo where we will see it all in action. So, without any further ado, let's jump right in. Each Vultr region provides its own VPC, an isolated layer 3 network that supports internal communication between instances. But when you need east-west connectivity across regions, you're often forced to fall back on public IPs. That means exposure, NAT configuration, and potential regulatory risk. Private inter-region communication should be encrypted, low latency, and as seamless as talking within a single subnet. That's where private peer-to-peer mesh becomes crucial, as it gives you full control of VPCs with the flexibility of global reach. If you're unfamiliar with how Vultr VPCs work, we recommend checking out our Tech Talk titled Securing Instance-to-Instance Data Transfer with Vultr VPC Networks first. It dives deeper into how VPC isolation works. Let's now break down the proposed architecture into four major planes. First is the network plane. Each Vultr region hosts a gateway node that participates in a full WireGuard mesh using Tailscale. These gateways advertise their local VPC subnet and serve as cross-region egress and ingress points. The mesh allows secure and private connectivity between regions, bypassing the public internet. The data plane sits underneath this mesh. Each Vultr VPCs contain both the gateway and one or more client nodes, which are the actual application workloads. Clients rely on the gateway to forward traffic to remote VPCs securely. Next is the control plane that consists of a headscale. Headscale is our self-hosted coordination server which acts as a central authority for managing Tailscale nodes, handling identity, key exchange, and route registration. Tailscale clients run on gateways creating WireGuard tunnels with other gateways based on the configuration received from Headscale. Next comes the routing layer. FRRouting propagates tailnet routes from each regional gateway to the respective client nodes, ensuring seamless service connectivity across data centers. This ensures that even if a new subnet is added to a VPC, the entire mesh learns about it automatically. Finally, for automation, we use Terraform to provision the entire setup, from VPCs in subnet to instances and startup script. Ansible then takes post-provisioning tasks like automating the configuration of Headscale, gateway, client nodes, and routing rules. And then comes Cloud Init, which installs and configures Tailscale, joins the gateway nodes to the Headscale coordination server, and sets up FRRouting for dynamic route propagation across the mesh. Let's now compare traditional VPN approaches with what we are building. A manual WireGuard setup requires you to generate and distribute keys manually, configure tunnel interfaces and routing per peer, manage NAT and firewall rules across regions, and update peers as and when network grows or changes. That's fragile, static, and non-scalable. With Tailscale and Headscale, the process becomes declarative. Nodes authenticate and fetch peer info from Headscale automatically. WireGuard tunnels are established peer-to-peer and encrypted end-to-end. Route sharing is handled through FRRouting and require no manual update. This let your mesh grow with zero-touch provisioning. And with Terraform, Ansible, and Cloud Init, both node provisioning and post-deployment configuration can be fully automated. Now that we have covered the basics, let's jump into a live demo. We'll provision a private mesh across 5 Vultr regions using the Terraform setup. You'll see how each region gets its own VPC, how a central Headscale server is deployed, how gateways are provisioned, client nodes are configured, and how Tailscale establishes tunnel without manual intervention. We'll also verify the connectivity across region by comparing public and private throughput. This will also demonstrate how the system behaves under real-world latency and bandwidth conditions. Going through the manual overhead of creating a private connection across multiple Vultr regions can be draining and time consuming. To streamline this, we have automated the setup using Terraform and Ansible. We have created a GitHub repository that contains Terraform manifest and automation script, the link to which is attached in the description below. The VPC peering Vultr region directory of this repository includes everything you need from infrastructure as code for provisioning to configuration script for setting up the mesh. This repository is structured to be modular and adaptable across different Vultr regions. Let's start by provisioning a Linux-based Vultr Cloud Compute instance. For that, open Vultr Customer Portal and navigate to the Compute section on Vultr. Here, click on Deploy Server. Select the compute type based on your preference. We'll go with shared CPU. Then choose a nearby region. We'll go with a compute plan that satisfies our setup requirement. One virtual CPU and 1 GB of RAM will be sufficient for our purpose. Then we'll go ahead and select the base operating system. We'll add an SSH key for secure remote access. Additionally, you can configure a startup script or apply a firewall group if needed. Then we'll provide a label to our instance. From the additional features, we can disable automatic backups because we at the moment do not require this. Then we'll go with a non-root user with sudo privileges. Once everything is configured, click on deploy and this action will launch a fresh Vultr Cloud Compute instance. Now that our instance is up and running, let's switch to the SSH environment to execute the remaining steps. Before we begin, please ensure that Terraform CLI, Ansible CLI and Git CLI are installed on your instance. Let's verify their presence on demo server. As we can see, our instance has all these three tools installed and ready to use. Let's officially begin setting up our environment. We'll first clone the code samples repository and navigate to the VPC peering Vultr region directory. One essential file here is terraform.tfvars. It includes all user-specific input values for the infrastructure. We'll now edit the template configuration of it. We'll first supply our Vultr API key, which will be used to authenticate Terraform to interact with our Vultr account and provision resources. We are defining a Headscale control server here in the Amsterdam region and using a non-root user with sudo privileges. The compute plan that we have selected for all our instances is 2 virtual CPU with 4 GB of RAM. The Headscale coordination server is here used as a control plane for Tailscale node authentication and configuration. The Tailscale instance block here defines Tailscale gateway nodes in each Vultr region from Atlanta, Melbourne to Bangalore, New York, and Amsterdam. Each of these subnets are associated with a unique private subnet, indicating connection with local regional VPC. Let's now save the changes and exit from this file. To kick off the provisioning process, we start by running Terraform init. This sets up our working directory by downloading the required Vultr provider, verifying the configuration, and preparing the backend for state tracking. This is a one-time initialization step unless provider version or backend changes. Next, we run Terraform plan. At this stage, Terraform passes over all the .tf files, reading variables, evaluating dependencies, and creating an execution plan that outlines what will be provisioned and where. In our case, the plan includes a unique VPC in each region listed in the Tailscale instances block, a Headscale control server deployed in the specified control region, a Tailscale gateway node in each region bound to its local VPC, a client node per region placed behind the same VPC as the gateway, an SSH key uploaded to Vultr and its private key injected in our project directory, a base64 encoded startup script attached to the client nodes, and a dynamic Ansible playbook named inventory.yaml file generated from a null resource. After the provisioning is completed, you'll see an output similar to this. Once we review and approve the plan, we run Terraform apply. This is where Terraform will interact with Vultr APIs to bring everything to life, from provisioning VPCs and instances to keys and metadata. When prompted, type yes to approve and apply the configuration. As you can see, the deployment was successful. Let's switch to the Vultr customer portal for a better view. Here you will see that a Cloud Init script has been injected to the Headscale coordination server for automatic configuration on boot. Similarly, a Cloud Init script has also been attached to the gateway node for installing and configuring Tailscale, joining the node to the Headscale node, and installing and configuring FRRouting. Client nodes, on the other hand, have received a startup script that bootstraps them after provisioning. As a final step, Terraform writes an Ansible compatible inventory.yaml file so that we can plug it into our automation workflows. Let's now run Ansible playbook to configure the private mesh connection. This playbook uses the generated inventory.yaml file to identify and group instances. It configures Headscale control server and all regional Tailscale nodes to form a fully connected private mesh network. If you would like to add more clients to this private VPC mesh network, you can do so by applying the target VPC and selecting the startup script named Headscale mesh init script while provisioning a new instance. This script currently supports Debian and RHEL based distributions. For other distributions, you can manually configure FRRouting or add static routes to integrate them into this mesh. So right here in the play recap, we can see that all 5 regions and the Headscale node have completed their task without any error. The change count indicates that the configuration was successfully applied, and with 0 unreachable and failed host, the private mesh network is now fully operational. Now that the mesh is set up and all nodes are connected via Headscale and Tailscale, the next step is to verify the integrity and performance of the inter-region mesh. We do this by running a separate Ansible playbook called network test.yaml, which benchmark connectivity between regions using both public internet path and private WireGuard based mesh managed by Headscale. Under the hood, this playbook performs ping test to measure latency and packet loss and IPERF3 test to assess bandwidth and throughput. After completion, Ansible creates network test results directory containing 3 key artifacts. Network results.txt is a full merge log of all tests executed between every region pair. Private results table.txt is a formatted summary of private mesh tests using Tailscale IP routed through Headscale managed WireGuard mesh. And public results table.txt is a formatted summary of public IP tests showing region to region performance over the public internet. Let's now check out public results table.txt. This shows high throughput due to direct routing over the well-optimized public backbone. Latency is relatively low but may fluctuate depending on peering. Let's look at private results table.txt. These tests uses Tailscale assigned IPs over encrypted WireGuard tunnels. Latency is comparable to public paths confirming correct routing. Throughput may be lower due to encrypted overhead or routing via user space networking. And that's how we deploy a fully connected private mesh across Vultr region using Headscale, Tailscale, Terraform, and Ansible. We have linked the supporting doc in the description below for you to refer as you set this up. To summarize, what we have built is a scalable, secure, and self-healing private network mesh across Vultr region. By combining Headscale, Tailscale, and FRRouting with infrastructure as code, we have created a platform that simplifies cross-region private communication without exposing traffic to the public internet. If you would like to replicate this production-grade setup on Vultr, you can get started today by claiming $250 in free credits on a new account using a promo link attached in the description below. Thank you so much for joining this Tech Talk. We hope this helped you rethink how you design multi-region architecture.